everyone, welcome to this video where we're going to explore the kineto-static modeling of continuum robots. I'm assuming you already have some basic knowledge of robotic modeling, so we won't spend time on the very basics. Instead, we will focus on how to approach modeling specifically for continuum robots. Let's get started. The kineto-static behavior of Cosserat rods is governed by several key sets of equations. First is the static equation. The static equation describes the rod's position and orientation. Next, the constitutive laws. They relate internal forces and moments to strains and curvatures. Finally, the kinematic equations describe how these internal forces and moments evolve along the rod. In this presentation, you will learn how to derive these equations in detail. Let us start by understanding how we model rods. The key idea is that rods are usually specified by their center line. The center line represents the path traced by the centroid of the cross sections as you move along the length of the rod. To describe how the rods behave, we introduce two coordinate frames. The first is a globally fixed frame which stays stationary in space and doesn't move around. And we call this frame I. This represented by the basis vectors E1, E2, and D3. The second one is a local or material frame. This is a frame which moves along the center line of the rod and sweeping as it goes. We call this frame M, and it is described by the basis vectors D1, D2, and D3. In the material coordinate frame, the directors D1 and D2 span the cross section, and D3 is orthogonal to it. Position of the central curve in global frame is defined as the vector P, which equals to x E1 plus y E2 plus z E3. Now let's take a look into the rotation matrix. Rotation matrix relate the local frame to global frame. From quaternion algebra, we know that given quaternions as a unit vectors q1, q2, and q3 plus a scalar part q4, the rotation matrix that relate the local frame to the globally fixed frame is given by the matrix R that's shown here. As you see, matrix R includes three columns, each are a three-dimensional unit vector, as you can see here. Here, one important thing is that since only quaternions of norm 1 represents pure rotation, the unity constraints need to be met. Now let us start with deriving the static equations. We're gonna use Cosserat rod theory to model the CR here. CR is an abbreviation for continuum robots. Cosserat rod theory is a beneficial theory to model rods with large deflection in the presence of forces and moments. Two sets of strains describe the deformation of Cosserat rod. One is the linear strain, which I'll denote as nu, and the other is the angular strain, which I'll represent that as kappa. Among the various existing definitions for measuring strains, Cosserat rod theory uses these two definitions. The first one states that derivative of the center line position with respect to the arc length equals to rotation matrix multiplied by linear strains. This equation represents the rate of the change of the position vector along the arc length. The second definition states that the derivative of the director vector di with respect to the arc length s is equal to the cross product of the curvature vector kappa with di. This formula, which is also known as Fresnel-Serret formula, describes how each director rotates along the rod's length due to the curvature. Looking at these two equations, you see that the derivative of the linear position is related to linear strain and the derivative of the angular position is related to the angular strain. So to get a physical sense of the linear and angular strains, some references says that we can assume these two strain sets as local and linear velocities, or in other words, velocities of the moving cross section along the central curve. Another point I'd like to add here is that the angular strain vector kappa is also known as Darboux vector. You may come across this jargon in references, so just know that the Darboux vector is the set of angular strains. Darboux vector is a concept used particularly in the study of curves and surfaces and describe the rotation of a moving frame along a space curve. In this slide, view Cosserat theory to get the static sets of equations as you can see here. Now let's get to kinematic equations. To derive the equilibrium equations, we use Newton-Euler law here. We consider an infinitesimal element as you can see here and write down the balance equations for force and moment for this element. The results will be these two formulas here. I'm gonna go in detail how we obtain these two in next slides. But before that, you need to know that M and N are internal forces and moments which are described in local frame, and Fx and Lx are external forces and moments defined in global frame. Now let's discuss in detail how we derived the kinematic equation shown in the previous slide. As shown, the force acting on the element include both internal forces and moments in the beginning and end cross-section of the element, and also the external forces and moments, of which here we consider them in their general form and apply their profile on the center line of the element. Now, if we write down the force balance, it results in this equation. This equation represents the balance of forces along the rod, where the difference in internal forces at 2 points S1 and S2 is balanced by the integral of the external force density over the segment. The equation you see here is the original integral form of the equation, which expresses the balance over a range between 2 points. What I need now is to convert it to a differential equation. To convert this equation to a differential equation, we focus on a small segment where the length S1 to S2 tends to 0. This effectively reduces the equation to a local analysis at any arbitrary point S. Taking derivative with respect to S needs to treat S1 as a constant and S2 as a variable. Here the variable is S. So considering S2 instead of a as a variable instead of a boundary allows us to differentiate the equation with respect to S. So let's take derivative of the force balance equation. By taking derivative of this equation with respect to S, we get the differential form of the force balance, which gives the derivative of the internal force with respect to S plus the external force equals to 0. Now let's get to the moment balance equation. To get the moment balance equation, we consider again the infinitesimal element shown here and write down the moment balance about the origin of the global frame, frame I. This gives us this equation. As you see, this equation includes contributions from the moments and the cross product of the position vector and internal forces from both the end and the beginning cross sections, and also the contribution from position vector and external forces and external This equation ensures that the net torque along the rod remains in equilibrium over the interval. Alright, now I'm gonna take derivative of this equation. Before that, I just rearrange the formula as you can see here. Next, I'll break it down into 3 parts and take the derivative of each part separately. So let us start with the first term. The derivative with respect to s of the difference between the moments at s2 and s1 is equal to derivative of the moment as a function of s. Let's go to the second term. To take derivative of the second term, we use the product rule. The product rule tells us that when differentiating the product of two vectors, we handle it step by step. First, we differentiate one vector while keeping the other constant, and then we switch. So the derivative of the cross product of the position vector and internal force equals to the cross product of the derivative of the position vector with internal force plus the cross product of the position vector with the derivative of the internal force. Now let's go to the last term. When taking the derivative of the third term, the derivative is applied to the integral and cancel it out. So the derivative of the integral equals to the cross product of the position and external force plus the external moment. Here I'm gonna take one more step and make the third term consistent with the second one. To do this, I'll use the force balance equation, and from that equation we know that the derivative of the internal forces equals to the minus external force. So substituting this equation into the third term gives the derivative of the third part equals to minus cross product of position vector and internal force plus the external moment. Finally, substituting these three terms in the original equation gives the moment balance equation as the derivative of the moment with respect to s plus the cross product of the derivative of the position vector with respect to s with internal force plus the external moment equal to 0. So far, we obtained the kinematic equations as you see here. What I want you to note is that this equation is obtained in the global frame. For example, in the first equation, we took derivative of the force vector in global frame, and the force vector itself is a local vector or a vector in the material frame. In the first equation, the external force is also defined in the global frame. In the second equation, moment and force vectors are defined in the local frame. The derivative here is in the global frame, and the position vector and the external forces are also global vectors. Now let's obtain the equivalent equation in the local frame. When taking derivative, the product rule is applied. So the derivative of the force vector in the global frame with respect to s equals to the derivative of ni's components multiplied di's plus ni's multiplied by the derivative of di. Now the first term is equal to the local derivative of force vector, and the second term can be simplified using the Fahrenheit-Serre formula. According to the Fahrenheit-Serre formula, I'm substituting the derivative of di's with respect to s with the cross product of kappa with di's. So step by step I get to this equation as you see here. So the derivative of the internal force in global vector with respect to s equals to the derivative of internal force in the local frame plus the cross product of curvature vector with internal force. The same applies to the moment vector as well. So taking derivative of internal forces and moments in the global frame finally yields these two equations as you see here. Alright, we were working toward obtaining kinematic equations in local frame. So far, we could get the global derivatives of internal forces and moments in terms of their local ones, as you see here. Another thing that helps us here is that the static equation. From the static equation, we know that the derivative of the position vector is equal to r multiplied by nu. Now I'm substituting these two into the moment balance equation. The first two terms here represents the derivative of m in the global frame, and in the third term r nu replaces the derivative of the position vector according to the static equation. As you can see, we have rotation matrices and their transposes multiplied by our global and local variables. Previously, we explained that the rotation matrix R maps local variables to the global frame, and accordingly, the transpose rotation matrix performs the reverse operation. So R transpose multiplied by R gives I matrix, which simplifies our equation to what you see here. So R transpose multiplied by R gives I matrix, which simplifies our equation to what you see here. Finally, our kinematic equations in the local frame obtained as you can see here. Now let's get to the last set of our equations, which are constitutive laws. We need constitutive laws that define material relationship by connecting the internal state of materials, such as strains, to their external responses. These laws are derived based on material properties. For Cosserat rods, the constitutive laws typically take the following forms. The force-strain relation says that the internal force at point S equals to the cross-sectional stiffness matrix multiplied by the difference of the current and the reference linear strain at that point. The moment-strain relation says that the internal moment at point S equals to the bending torsional stiffness matrix multiplied by the difference of the current and the reference angular strain at point S. And here the stiffness matrices are defined as you can see here. Finally, we got all required sets of equations, including static equations, constitutive laws, and kinematic equation that allows us to model kineto-static behavior of Cosserat or continuum robots. And as you can see here, the number of equations are 19 that include 6 three-dimensional equations plus 1 unity constraint that apply to the quaternions, and the number of unknown variables is the same, 19. You can see that our unknown variables include position vector, quaternion, kappa, and internal moments and forces. Thank you for being with me. I hope this tutorial helped you understand how we can model kinetic behavior of continuum robots.